Okay, good morning, everybody. Let's start our class. And today I'm going to talk about chapter 12, and which is called time series model. Okay, I think you all remember that we have done chapter 9, which is called time series data. And we understand the characteristic of time series data, especially time series data do have serial correlation problems, okay? And we learn how to test the serial correlation, and we learn how to uh, uh, diagnose uh, the serial correlation, and also we know how to fix it, okay? And today in chapter 12, we are going to talk about the time series model. All right. So the purpose of this chapter is to provide an introduction to a number of interesting models that have been designed for time series data. Especially, we are going to introduce two types of time series models. One is called, okay, let me share. Let me share my screen, okay? Okay, we just say that the purpose of this chapter is to introduce the time series model. So especially, we are going to introduce two types of time series model. One is called distributed lag model. Okay, let me show. Okay, this is called distributed lag model. I think we already mentioned this kind of model in chapter 7. Okay, we talk about this model, but we just introduce. Sometimes we do have the x variable, which has the lag instead of the current period. Okay, so time series data usually we express as yt. T means the time. Okay, and the x variable is x1, and also show the current with t. But when we have the t minus 1, is like a 1 period, means the one previous period. Okay, so in this model, we do have x1 and x2. X2 is the current data, and x1 is t minus 1 data. Okay, and this is what we call distributed lag model. Okay, we will introduce that in details later on. Okay, and the second one, the second model we are going to talk about is called dynamic models. Okay, you see the difference between the distributed lag model and the dynamic model. Okay, so if distributed lag model, we do have X lagged independent variable appears on the right-hand side of the equation. Okay, such as 12.1 and 12.2. Okay, so 12.1 is the model with two lags. So t minus 1 and t minus 2. But if we can extend to many lags, and which we call is a more general distributed lag model. Okay, and so this is the expression is like equation 12.2. So in other words, instead of t minus 2, we can extend it to t minus p. So p is the maximum number of the periods x is lagged. Okay, so in other words, if I have 10 lags, means p equal to 10. Okay? However, the other called dynamic model, okay, which we have lagged dependent variable. Okay, instead of lagged independent variable, we have lagged dependent variable appears on the right-hand side of the equation, such as 12.3. All right, as you will see later, that a dynamic model can also be represented as a distributed lag model. And in fact, both models are in a class of dynamic models. And this implies that the impact of the independent variables can be spread out over a number of time periods. Okay? Okay, now let's consider why it is important to have the independent variable spread it out over a number of time periods. Consider the impact of advertising on sales. Okay, most analysts, let me go back to this one. Okay, and consider the impact of advertising on sales. So if we say Y is the sales, X is the advertising. And most analysts believe that people remember advertising for more than one time period. So advertising affects sales in the future as well as in the current time periods. As a result, models of sales should include current and lagged values of advertising. Therefore, distributing the impact of advertising over a number of different lags. So if we have this Y as the sales, X as advertising, and 12.1 say the advertising affect the Y with 2 time periods. And if you think the advertising is not only just two periods, it can be extended to many periods. For example, P equal to 5. All right. And if you want to turn to your book on page 383 in chapter 12, okay, so the model, okay, like this, okay, the model like this is called simple. This is called a simple lag because just only one. And OLS can estimate without any additional complications. In other words, with this one, OLS still work. Okay, with this model, OLS as estimation, it still works. And this is called simple lag. Okay, we do have more complicated case. Is when independent variables impact is expected to be spread out over a number of time periods. Okay, so it's something like this. Okay, and let's see. Let's see. Okay. How do you how do you explain the beta 1 and beta 2 in 12.1 equation? Okay, for example, I think you all know how to express this as beta 1, right? And beta 1 measures the effect of 1 unit increase in X in the current periods, okay, on the same periods of Y, holding other times X constant. But beta 2 means the effect of 1 unit increases in times in like 1 times on this times of Y, holding other X, holding other periods of X constant. Okay? All right. And so for example, suppose we are interested in studying the impact of a change in money supply on GDP. And the theoretical and empirical studies have provided evidence that it takes time for the economy to react completely to a change in the money supply. So it takes 2 years. Some of the effects will take place immediately. Some will take place with a lag of 1 year, and the rest will occur with a lag of 2 years. So in such cases, the appropriate econometric model would be like equation 12.1. Okay, so Y would be the GDP and X will be the money supply. Okay? And you'll see that equation 12.1 on the right-hand side, X variables appears 3 times, the current and the first leg and the second leg. Right? When we estimate the model using OLS, something like this one, equation 12.1 or 12.2, what kind of problems as so far we have learned? Okay, do you expect what kind of problems using the OLS estimation with equation 12.1 or 12.2? Anyone can answer the questions? Any one of you? Remember, we learned this one before. This is X variables, just with the same X variables, but different time lag. Any questions or any problems any problems pop on your mind? You all remember we learned multicollinearity. What do we mean by multicollinearity? multicollinearity means there's a highly correlation among the independent variables, right? So if we do have the example for money supply to affect the GDP, so xt and xt minus 1, xt minus 2 is the same money supply, but different time periods. So is it possible to involving the multicollinearity problems with equation 12.1? We would guess, right? The highly possible to have multicollinearity problem.
Yes.
But if we use the OLS estimation to estimate the model with multicollinearity problems, what will happen? What will happen to that? Okay, if you go to the chapter 8 and review multicollinearity problems, then I think you will recall all these problems. Okay, and so we say that estimation of equation 12.2 with OLS causes a number of problems. Okay, the first one is various legs of X are likely to be severely multicollinear. Okay, and as let's also go back to the effect of the example we just showed. Y is GDP and X is money supplied. Do you expect the impact of those money supply to GDP will decrease as the length of the lag increases? In other words, the current money supply will affect the GDP the most. Then by the time, then the effect will decrease. Therefore, the beta 2 are expected to smaller than beta 1, and beta 3 is smaller than beta 2. Okay? Okay, so let's see. If we use the OLS to estimate 12.2, there's no guarantee that the estimated betas will follow smoothly declining pattern theory would suggest. So in other words, according to the theory, the beta 3 should be the smallest and should be smaller than beta 1. Okay. And if we do run the regressions, we may not have the same result as the theory expected. Okay? All right. We'll see that example later on. Okay? The third problem is the degrees of freedom tend to decrease for two reasons. Each lagged X has a coefficient to estimate, and each lagged X decreases the sample size by 1. Okay, there's two problems with the degrees of freedom. Let's go back to the equations 12.1. Okay, if I do have t minus 1 and t minus 2 with the same X, therefore, for the number of independent variables, K increase by the number of lags. Okay, and excuse me. Okay, then with the data, since we need to have t-1 and t-2. So if we have the sample size with 100, so for example, we have a sample size of 100, since we need to have t-1 and t-2. Therefore, for the whole models can be used, I mean, the data need to reduce the 2 time periods. So the sample size should decrease to with 2 years, okay, with the t-1 and t-2. This is what we say. Each lagged X decreases the sample size by 1. Any questions so far? Any questions?
Professor, can you repeat again, please?
Okay, let me explain it. Okay, so if I do have sample size is 100, okay, with the equation 12.1. Okay, if I don't have the lag, I mean x t-1 and t-2, okay, I can use 100 sample size. I can use 100 sample size with xt and yt. So since I need to expect beta 0 and beta 1. So how many degrees of freedom do I have? When we say the degrees of freedom, we are talking about the degrees of freedom of standard errors. I mean the t-test. T-test. What is the degrees of freedom with just only xt as an equation with sample size of 100? It's usually 100 minus 2, right? So it's 98. Excuse me. Any questions with this one? But now I have beta x t-1 and t-2, means I have 2 lags. Therefore, my independent variable increased 2 variables. One is x with t-1 and x with t-2. Therefore, in the equation 12.1, I have 3 x variables. Okay? With 4 estimation, beta 0 from beta 3. So what's the degrees of freedom becomes? Is reduced from 98 to 96. Because I'm using 100 minus 4 is the degrees of freedom for t statistic, right? This is what we say. Each lag x has a coefficient to estimate. Therefore, degrees of freedom decrease. Do I make myself clear? Excuse me, anybody? You all understand what I'm trying to say?
Professor, I think we will study by ourselves, I think we can. Now we don't understand, but we will get on it.
How about the rest of the classmates? Anybody answers? You understand what I'm trying to say? I'm trying to explain that estimation of equation 12.2 or 12.1, okay, with OLS will cause some of problems. I think the first one and the second one is okay for all of you, okay? But the third one, the degrees of freedom tend to decrease for two reasons. Okay? So degrees of freedom will decrease, okay, by these two reasons. The one is if we increase the lags of X variables, the model will increase the number of independent variables. Therefore, decrease the sample degrees of freedom. Okay? And the second one is each lag X decreases as the sample size by 1. What does that mean? Means if I have 2 time lags, okay, although I have 100 sample size, in order to we all know that in regressions, we do need to have the sample on the both right-hand side and left-hand sides in order to run the regression, to have complete the sample for both y variables and x variables. So in other words, if I have 2 periods lag, means I need to sacrifice 2 years data in order to run the regressions. So if I take 12.1 as an example, okay, without t minus 1 and t minus 2, I can, my sample size, 100 sample size data, in this case, I do have 100 minus 2 equal to 98 degrees of freedom for the equations. But if I increase 2 time lags, okay, therefore, I have 4 betas has to estimate it. And at the same time, I need to sacrifice 2 years data with t minus 1 and t minus 2. Okay? Therefore, my degrees of freedom becomes 100 minus 4 and minus 2 years. So it becomes 94. 100 minus 4 minus 2. So it's 94. So my degrees of freedom decrease from 98 to 94. Is it okay? This is what I mean. For the third parts, the degrees of freedom tend to decrease for 2 reasons. One is from the number of lag X variables. The other one is from the lag X will sacrifice the sample size. Okay? Okay, may I go on? Okay. Okay, now let's see 12.2 on page 385. for dynamic models. All right. The simplest dynamic model is 12.3, like this one. Means that I do have one x variables. The other one is the lag of the dependent variable. Okay. And okay, now I'm going to say, or I'm going to introduce or explain which is more complicated and I want to express how the dynamic model can be represented as a distributed lag model. Okay? All right. First, look at 12.4. The 12.4 is using the one lag of 12.3. So in other words, one lag. Okay, so yt becomes t minus 1. xt becomes t minus 1. And yt minus 1 become yt minus 2. And ut becomes ut minus 1. I think there's no questions, right? So 12.4 is one lag of 12.3. Okay, now substitute equation 12.4 into equation 12.3 means I replace yt minus 1 here into, I'm using this whole parts because this is expression of yt minus 1 into the place of equation 12.3 of yt minus 1. You see what I'm saying here? Therefore, becomes 12.3 equation becomes, look at this one, just yt, then alpha 0, beta 0 xt. There's no change about it. But you have to replace this y minus p with this whole parts. Therefore, you can see lambda, then the whole parenthesis here is 12.4. Any questions so far? Okay, right? Then look at 12.5. This is equation 12.5. Okay? And rearrange it. How to rearrange it? Like this one, lambda alpha 0 is a constant. Okay? So I will put this with alpha 0 together. Okay? Then x1t is beta 0 and xt minus 1 using lambda beta. Okay, the coefficient is lambda times beta 0, etc. And yt minus 2 is lambda squared. And this ut with lambda and also t minus 1 with lambda and also the original ut, put them together as an error terms, which becomes 12.6. I think all these equations also shown on the textbook on page 385. Okay, now 12.7 is just exactly as what we have 12.6, but using this whole parts and denoted as alpha 0 star. Okay, and this whole parts as ut star. Okay, So in other words, with original 12.3, the simple dynamic models can be 12.3 just one xt, right? And it can be expressed as one more x with t minus 1. Okay? And also xt minus 2. But with uh, lambda and also yt minus 3. So in other words, if you do it again and again, go to the same process as I just did. Okay, eventually you can express a dynamic model as an distributed lag. So which means that the original so the coefficient of lag x follows a clear pattern. Then comparing 12.2 to 12.7. Okay, so we compare this 12.2 to 12.2 to 12.7. Okay, then we know that the beta 0 was the original xt. Okay, and then beta 1, started from beta 1, can be expressed as the lambda times beta 0. Okay, then beta 2 is become to the lambda square times beta 0. And beta 3 is lambda 3, third power, times beta 0. And so on, up to beta p equal to lambda's pth power times beta 0. Okay, I'm going to stop here for a while. You understand what I'm trying to express so far? You understand what I'm trying to say? In other words, what I just did is the distributed lag model. The general form of the distributed lag model is like equation 12.2. Means that the right-hand side, there's many lags of the x variables. Okay? And for dynamic model, it's just one current x with one previous dependent variables. But the dynamic model can be expressed as a distributed lag model. Means that I will not have the yt minus 1 anymore. I will have continuous to have that distributed lag model. Therefore, I would becomes like this way. Okay, and the equation, I mean the coefficient of all these lag x variables can be expressed as the original coefficient of the xt times the lambda, which is, this is lambda, right? This is called the coefficient, the one lag of the y variables. Okay? Any questions about that? So I think this one is important. Okay, this PPT for 12.2 and the 12.8, they are the same. Okay, so as long as lambda is between 0 and 1, then we say that since lambda is between 0 and 1, and they do have the same beta 0. Therefore, the coefficient is smoothly declined. Any questions so far, my dear students?
No, Professor.
Are you get lost? Are you lost?
A bit
Huh? Excuse me. You're with me?
lost a bit, but will review.
Huh? I'm sorry. Excuse me. I cannot hear quite clearly.
Got lost a bit, but we will review.
Oh, let me go back to, okay. Anybody want to ask questions? Or anybody want to say something that, if you don't understand it, it's hard to go on. Is all the PhD students okay?
Yes, Prof. Continue, Prof.
Huh?
Okay, Prof.
No problem.
No problem, Prof.
Excuse me, I cannot hear clearly.
Oh, my wife, maybe. Hello?
How about my master students? Say something about it. I know this chapter 12 is a little bit difficult. Maybe it's difficult for all of you, but if you review it or study it, I think it's still fine. But I would say that chapter 12 is really hard. Okay, all the topic is pretty new for all of you. I'm not sure about the PhD students. Maybe you're easier than the master students. Daniel, would you like to say something about it? You understand what I'm trying to say?
Yes,
Is it okay?
it's okay for me.
Okay, all right. How about Esther?
I think maybe I need more time to
To
read
read
the
it?
textbook.
Okay. And how about Linda?
Maybe I will look at the record again.
Okay, Catherine?
Yeah, I'm okay for this part.
Okay, okay. But make sure, read this chapter 12 after the class. Okay, for all of you, okay? All right. How about Moody? Moody.
Yes, Prof.
You all learned this time series data, time series model in other
Yes.
classes?
Yes, Prof. What you mean? Pardon?
I don't hear you.
Yes, Prof.
Eileen. Oh, okay, okay. Thanks. Eileen?
Yes, Prof.
Yeah, you understand what I'm trying to say this morning? Okay, all right. So if you can understand it, and why don't I just use an example? Okay, I think it's necessary to use some data and run the data. and to see all this, to see all this theories. Okay. All right. And let's see. So why don't we just stop here for a while? Then we'll come back later. Okay? It's about the time for this session.
Okay, Prof.
Okay?
Okay, Prof.
All right. I'll stop the recording first.